Good afternoon, everyone. I am Laura Sipe, the Director of Strategic Engagement and Alumni Relations for the College of Engineering, and I'm here to welcome you to our Engineering Cures for Cancer presentation. We are excited to be launching this new series today because for us, it's our opportunity to showcase for you the partnership between the College of Engineering and the Comprehensive Cancer Center at The Ohio State University to form the brand new Center for Cancer Engineering. In just a moment, you will hear from Dean Williams to provide a little bit of context on why the center was formed and why it's a priority for the college. And then you'll get to hear some of the amazing research of our engineering faculty who are working with the center. But before I turn things over to the Dean, I want to take a moment and let you know that if you do need access to closed captioning services, please click the closed captioning button on the bottom of your screen. I also want to thank those of you who submitted questions in advance. So the second half of our presentation, we will make sure to spend some time addressing those questions. But if you didn't submit one in advance, don't worry, there's still plenty of time during the conversation today for you to ask your questions. Just make sure to put them in the Q&A button at the bottom of your screen so we can see them. So on that note, I am happy to turn things over to our Dean, David Williams, for a little bit of insight about the Center for Cancer Engineering. Dave?
Thank you, Laura. And if somebody could start my video, that would be really good. There we go. Thank you very much. And hello to all of you. There's some very familiar names out on that list there. So good to see you. Sorry we can't be here in person, but in fact, we've probably got a much better turnout because of this medium. So there are some silver linings to these clouds that we're working with. Let me start by thanking Rafe Pollock. Rafe is the director of the Comprehensive Cancer Center, the James Comprehensive Cancer Center, which many of you know. And without his support and without his commitment to the interface between cancer and engineering, we wouldn't be celebrating the creation of this new center. And it's an integral part of the proposal that the James put in to the National Institutes of Health, the National Cancer Institute within that organization. And they were just awarded a renewal of their major comprehensive cancer grant, and cancer engineering was an integral part of that. So that's really the reason why we're partnering with the James, because they are a leading cancer research operation, and they are looking for innovative technologies, data analytic approaches to advance the understanding of cancer biology, to enhance cancer prevention, enhance cancer diagnosis, and better treatments to improve the lives of those people fighting cancer. And in so many of those areas, engineering plays a role, as you will hear. I should also call out Dorota Brzezinska, Associate Dean for Research in the College of Engineering, Matt Ringel in the Comprehensive Cancer Center, and Jonathan Song in our Mechanical and Aerospace Engineering Department as the leaders in this joint operation. Engineers solve problems, and many of the problems that are facing cancer researchers and cancer patients can be addressed with modern engineering technology. In the College of Engineering, we have several major research thrusts in our strategic plan, including materials, manufacturing, and medicine. And you'll hear today how in this cancer engineering partnership, as part of our medicine engineering strategy, then new materials are playing a role, and new manufacturing methods are playing a role, as well as new methods of characterizing materials. And our researchers will speak about those three different areas. The center's goals in the long run are to increase seed funding for promising areas of research, train the next generation of cancer engineering researchers, and attract industry research and development collaborations. And the way the center carries out these parts of its mission are obviously through the work of extraordinary researchers. And I'm going to give you a glimpse of that, or I'm going to introduce those who can give you a glimpse of that today. So let me start with Jennifer Leight, Assistant Professor of Biomedical Engineering, who's replicating a patient's tumor in the lab to create a personalized medicine approach to treating it. Jennifer.
Thank you, Dean Williams, for that introduction. And I'm really excited to be here today to share some of the work that we're doing in my lab. I'm an assistant professor in the Department of Biomedical Engineering. I joined OSU in 2014, coming from the University of Colorado Boulder, where I completed my postdoctoral training. But I'm a native Ohioan. I was born in Columbus, and I grew up outside of Cleveland. And today I'm going to tell you about the work that my lab does, building engineering tools to study cancer cell invasion. So the spread of cancer from the primary tumor site to distant sites in the body is called metastasis. And it's this spreading that's responsible for over 90% of cancer-related deaths. In order to spread, the cancer cells must break out of their surrounding environment, which is full of extracellular matrix proteins. Here is a microscopic image of a tumor. You can see the tumor cells in purple, and these extracellular matrix proteins are in pink. And so the cells have to travel through this pink area to get to other sites in the body and spread. And here is another microscopic image of a cancer cell surrounded by these extracellular matrix proteins that you can see these proteins form a net. And so for the cancer cells to spread, they have to cut through this net and escape the primary tumor. And one way they do this is by using enzymes called matrix metalloproteinases, or MMPs. And so you can think of these as scissors that the cells use to cut through these nets and invade and spread to the rest of the body. And so one way that we can help to stop the spread of cancer would be to block these MMPs and to stop them from cutting these protein nets. Another question that remains is we don't really understand how cancer treatments affect these MMPs and whether certain treatments might be better at stopping this cutting action. And so one thing that's preventing scientists from making progress in this field is that we don't have tools to measure the activity. And so my lab builds tools to address this problem. And so these tools that we make light up when these protein nets get cut. And so we can measure that light, so we can quantify this MMP activity, and then we can also localize where that activity is happening. And the way that we do this is by making these fluorescent peptide biosensors. So this black here is showing you a peptide that can be cut by these MMPs, and it has a fluorophore and a quencher. And so when the peptide is cut by the MMPs, then we get an increase in fluorescence that we can measure. We make these peptides in our lab using a solid phase peptide synthesizer. So this machine uses microwave technology to build these peptides amino acid by amino acid. And we're using these sensors in a number of different ways. One way we use them is to study cancer cell invasion. So here you can see a cell invading into the matrix, and as it cuts that sensor, it lights up green. We're also using it in a similar way to those microscopic images I showed you at the beginning. And so here the green is showing where within the tumor we have that MMP activity. And then we're also using this technology for high throughput drug screening assays. So here is one project that we're using these sensors. So we have been using these sensors for a while in the lab to study cancer cells, but I was really interested in understanding how individual patients might have different levels of these enzymes and how drugs might affect those levels. And so we teamed up with a medical oncologist, Dr. Daniel Stover, and a plastic surgeon, Dr. Clara Lee, who specializes in breast reconstruction after cancer treatment. And in this project, what we do is we're able to get tumor samples after a tumor has been surgically resected from a patient. And we take these samples and we put them in a hydrogel system, a 3D engineered environment that mimics the environment the tumor cells experience in the patient. And within this environment, we have our biosensors. And then we can treat the different tumor samples with drugs and see how it affects that MMP activity. And the eventual goal is to be able to identify drugs that will be most effective for patient treatment. And so here you can see an example of some of these patient tumor samples being grown in our hydrogels. And so from one sample, we can grow anywhere from 50 to 100 tiny tumors and treat them with 20 different cancer drugs or different combinations of drugs. And so right now we're investigating how chemotherapy affects this cancer cell MMP activity with our eventual goal to use it in personalized medicine applications. Here's another example of how we're using these biosensors. So this is a collaborative project with Dr. Raphael Pollack, who's a renowned surgical oncologist. He works on sarcoma as both a surgeon and as a researcher. And so we had previously helped his lab to show that there is this increased MMP activity in liposarcoma. And so now we're using that to develop a drug delivery platform using that increased MMP activity within the tumor. So what would happen is that after the patient has their tumor surgically removed, we would implant this hydrogel. It's a material like Jello. And within this hydrogel, we have our peptide sensors. And attached to that sensor now we have a drug. And so when we have that increased MMP activity that cuts that peptide, we'd have drug release. So right now we've identified a peptide that's cleaved more by the cancer cells and as compared to normal cells. And now we're working on translating this technology to animal studies and eventually to the clinic. And one final example of how we're using these sensors is a collaboration with Dr. Alexander Skardell in the biomedical engineering department. His lab builds metastasis on a chip models using microfluidic technology. And so what Alex's lab does is they build these models where they can replicate the primary site. Here they're studying colorectal cancer, and then they can also have other chambers that replicate metastatic sites like the liver and the lung. And they label these cells in red, and then they can track them and see where they go and study the process of metastasis. And so now we're using our sensors within this system to understand how MMP activity is contributing to metastasis. And so I'd like to end just by sharing a little bit about why I think OSU and this new Center for Cancer Engineering is such a special place and so powerful for doing cancer research. And really it's about the people and bringing together scientists from different fields, engineers and physicians to tackle these tough problems in cancer research. We're also able to recruit really excellent students and trainees who do most of this work and a lot of times bring the most innovative ideas. And we can't forget the patients who are fighting this terrible disease and volunteering for these clinical trials and donating their tumor samples so that we can study them in the lab. And so what makes OSU different than a lot of other large universities is the physical proximity that brings all these people together. So here's a map, a campus map of OSU. And just to orient you, here's the shoe where Brutus lives. We also have the oval. This is the main campus where engineering is located. And the medical center is close by. It's only a 10-minute walk away. And so this really fosters that interdisciplinary collaborative research. And so here is a new building we have on the engineering campus that houses biomedical engineering and material science, Fontana Labs. My lab is located here in the Biomedical Research Tower, which is across the street from the James Cancer Hospital. And so it's really this proximity that brings us together in this fight against cancer. So thank you for your time.
Thank you, Jennifer. We have time, so I'd like to ask you to answer just a couple of small questions. First of all, it's embarrassing to see that the head of the Comprehensive Cancer Center, Rafe, is working with you actively in research. The same cannot be said for the Dean of Engineering in being involved in any active research. So well done, Rafe, and keep that up. If you were to pick one thing, Jennifer, that highlights how the presence of such a comprehensive cancer center within walking distance has revolutionized your ability to do this kind of research, what would an example be?
So before I came to OSU, I really was only using cancer cell lines, and I didn't have access to patient tissues. And everybody's cancer is so unique, and it's really important to be able to study these live tissues from patients, and it's really elevated my research. And being surrounded by cancer biologists and physicians and engineers, we really are working together to study each patient's individual cancer.
Yeah, this personal care, personalized medicine seems to be a theme at the Comprehensive Cancer Center. You mentioned particularly your work on breast cancer and colon cancer. Is this approach applicable to every cancer?
So it's applicable to a lot of cancers. So most cancers are carcinomas, which are cancers of epithelial cells. And often breast cancer, fundamental discoveries are made in breast cancer and then translated to these other kinds of carcinoma cancers. So prostate, colorectal, renal cell cancer, things like that.
And you're obviously partnering with many physicians and researchers at the Cancer Center. How far is your work away from actually influencing the treatment of patients and ending their cancers?
Yeah, so we're still a little bit ways away. So we've just now developed this technology to culture the patient cells, and then we want to make sure that anything that we do is safe. So we're probably around 5 years away from really being able to affect a patient's treatment.
Okay, Jennifer, thank you so much for all that insight, and it was very clear. I actually understood most of it, which is rather amazing for a dean, but your partnership is truly what makes the College of Engineering the sort of leaven in the bread of Ohio State research. We can apply engineering technologies in so many different ways. So thank you very much for what you do, and keep up the great work. So. Next, I'd like to introduce Husnain Hussain Ahmadabad. My pronunciation is appalling, but Hussain is a postdoctoral scholar in integrated systems engineering, and within that department is the Spine Research Institute, which is a long-standing partnership between the College of Engineering and the College of Medicine and the Spine Hospital within the College of Medicine. So Hussain, please introduce yourself and tell us more about your research.
Yeah, thank you, Dean Williams, for the introduction. What happened? Are you able to see my screen?
We sure can.
All right, let me try again. Okay. Okay, I apologize for that. Yeah, it is with my privilege to be invited by the college and be part of this panel. I got my PhD in systems engineering from Ohio State, and currently I'm one of the postdocs at the Center for Cancer Engineering and Spine Research Institute. My research is primarily focused on developing a data-driven predictive framework to understand spinal fractures in cancer patients. Spine is the most common site of tumor metastasis in cancer patients, if it's given enough time. In a spine cancer, normally tumor damages bone tissue, eats away part of it, and that causes significant amount of back pain, which is aggravated further as patients receive radiation therapy. So optimizing treatment strategies could drastically improve quality of life in cancer patients. To address these issues, we take a collaborative effort between the College of Engineering and College of Medicine at the Center for Cancer Engineering. So today I will touch upon the different steps of our framework. So we start off with preparing a segmenting CT and MRI images of the patients to localize the locations of any lesions or abnormalities in the vertebra. These images are annotated with the help of the doctors, the radiologists that we are collaborating at the radiology department. After this annotation, we follow two synergistic tasks. First, based on the anatomical information of the patients, surrogates, or should I say, human models are selected to perform daily life activities. This will eventually help us determine the biomechanical loads applied to the spine. We do this using the motion capture cameras and EMG-driven measurement technology at the Biodynamics Laboratory within the Spine Research Institute. Next, leveraging a comprehensive database and novel machine learning algorithms, a detailed geometrical model of the vertebra is built within the computer. So everything is done virtually. Coupling these, and after that, coupling these two steps together, we can eventually come up with a model or a digital twin of the vertebral bodies. This will help us to make prediction whether the spine is going to get fractured under a specific type of loading. Based on the current situations of the patients, later the neurological surgeons that we collaborate might suggest to perform surgical operations such as vertebroplasty. For those of you that are not familiar with vertebroplasty, it is an operation where essentially a biopolymeric cement is injected within the vertebral body in order to stabilize it, mechanically fix it. It is a life-saving operations. However, it sometimes leads to complications such as the subsequent fracture of the spine after the operation. So our goal here is to minimize some of these complications through detailed computational fluid dynamics modeling. Currently, we are collaborating closely with some of our colleagues at the biomedical engineering department in order to come up with a validation scheme, or should I say a proof of concept in animal studies or cadaveric human specimen. And yeah, this work is being funded by the Center for Cancer Engineering, and we have made significant progress since day one. And we have a couple of grants proposals submitted because with the help of the center. So, and I'm really grateful for that. And with that, I thank you everyone for your attention.
Thank you, Hussein. And there are some fine examples of new materials and new manufacturing processes to address this extraordinarily complicated issue. Now, you're a postdoctoral researcher. Perhaps there are many on this call who don't know what a postdoc is and how it's a step in your career to move forward. So could you explain that perhaps a little more?
Certainly. I think as a postdoctoral scholar, being at the Center for Cancer Engineering has provided me with great opportunities to challenge my engineering knowledge for a real-world cancer-related topic. Since I have started on this cross-disciplinary research upon my graduation, I have worked with several scientists, physicians, clinicians, surgeons, and radiation oncologists. And this has actually helped me to learn how to effectively communicate with people from other disciplines, understand their problem, and come up with solutions. And that has been really instrumental in the progress of my development of my research.
So thank you. Now, you've shown how you can remanufacture parts of the body that cancer has eaten out of the spine. Is this technology applicable to other parts of the body where the cancer has destroyed the tissue?
Yes, I think that the concept of digital twin or digital modeling within the computer can be essentially translated to any other human organ, assuming that we incorporate the appropriate physics and biology depending on that organ. Of course, that necessitates having people working from different disciplines and collaborate with each other. And some of the personalized algorithms that we have developed in order to reconstruct the vertebral anatomy could certainly be used on other applications such as scaffold design in bone tissue engineering or etc.
So, and the same question that I asked Jennifer, is this technology already being used in patients to replace parts of spines?
We use patient's data in order to develop the framework. In the beginning, when we mapped out our algorithm, we use the patient data in order to develop everything. However, right now we are in the process of validation with some of our colleagues at the biomedical engineering department on animal subjects. And in order to be implemented for actual patients, it might be a long way.
Okay, then that's what research is all about. So
Exactly.
again, Husnain, thank you so much for explaining that. That's just extraordinary technology. I'd now like to introduce David McComb, Professor of Material Science and Engineering and Director of the Center for Electron Microscopy and Analysis, where cryo-electron microscopy is becoming a crucial tool for researchers discovering and developing targeted drugs for cancer. David.
Thank you, Dave. I'm really excited to have the opportunity to talk to you today about the role of cryogenic electron microscopy in the study of cancer biology. But before I do that, let me say a brief introduction about me. So I grew up in Ayrshire in southwest Scotland, just a few miles from the Irish Sea. That's the view looking out into the islands on the west coast of Scotland. I did my bachelor's in chemistry at the University of Glasgow, and then PhD in chemistry and physics at the University of Cambridge. A brief trip out to Canada for a while as a postdoc, and then returned to faculty position in Glasgow, then Imperial College. And then at this point, my research has really been driving towards developing advanced electron microscopy techniques to really probe chemistry, structure, and bonding on the atomic scale. I was just inspired as a student to the fact that we could actually use techniques where we could see atoms, we can see how they bond to other atoms, and we can learn about structures. And so that then led me in 2011 to be honored to join the ranks of Celtic Buckeyes over here, and even more honored to be the inaugural director of the Center for Electron Microscopy and Analysis here at The Ohio State University. We opened our doors in 2013, and that represented roughly a $20 million investment in a world-class instrumentation and infrastructure. And CMAS is truly a remarkable place. We really believe this is a world hub for advanced microscopy across all scientific disciplines. We have capabilities that span all the physical and the life sciences. And that's one of the things that really makes us unique globally, is that we really bring together world-leading capabilities in physical and life sciences into a single center. We host nearly $39 million worth of instruments, and OSU, we're honored to be the home for an over $9 million investment that OSU placed of its own funds to establish a capability in cryo-electron microscopy. So let's turn to cryo-electron microscopy and talk a little bit about this technique. Just as a word of introduction, this truly is a remarkable time in structural biology. Many would describe it as it's really the second golden era in structural biology. Cryo-electron microscopy is a type of microscopy that exposes samples at extremely low temperatures to a beam of electrons, as we would see on the right-hand side here. And the way that those electrons interact with this sample results in scattering that allows us to study the structure of the molecules. It's really a crucial tool for researchers in the disciplines of structural biology to study proteins, nucleic acids, other biomolecules, and it really is the basis for drug discovery in cancer. Advances in the technology and the software have really meant that cryo-electron microscopy has come on really leaps and bounds in the past decade, allowing scientists to see structures of these macromolecules truly on the atomic scale, and resulted in the award of the Nobel Prize in Chemistry in 2017. So how do we actually do it? We take samples, and the samples are frozen at cryogenic temperatures as low as minus 180 Celsius, and we then examine them with high energy electrons. The samples, because the samples are frozen, the way that the electrons scattered by that sample give us information about the 3D structure, but most importantly, by flash freezing them at such low temperatures, we basically preserve the molecules in a thin liquid frozen hydrated film. The molecules are in their near native state. And so that really is allowing us to study the structure of the molecules as if they were in the cell themselves. Now, there's really three techniques that we associate with cryo-electron microscopy. First of all, we have cryotomography, and this is similar to the types of tomography that you might experience if, at the dentist, a dental surgeon, or even if you've had a broken bone or something and you've had to have a CT scan. What we're going to do here is we're going to take a thin slice of our cell, frozen, and we put it into our microscope, and now we tilt it and we image it at multiple orientations. And we take those images and we reform them into an image in 3 dimensions. And here's one example showing how cryotomography is being used to study platelets from normal versus ovarian cancer cells. So platelets are small multifunctional cells that circulate in the bloodstream, respond to vascular lesions. And in this example, what researchers have been able to show is how they can identify microtubules and mitochondria in patients that have been diagnosed with ovarian cancer, and show how these are distinctly different to those in control samples. The second example of technique that we can use in cryo-electron microscopy is called single particle reconstruction. And this really has revolutionized structural biology. In this case, what we're going to do is we freeze thousands of molecules in that vitreous state, and then we're going to take tens of thousands, if not even some cases, hundreds of thousands of molecules, and then we're going to take all those images and reconstruct them to see the 3-dimensional structure. In a sense, this is just a different type of tomography. The assumption is that every molecule in the solution is identical, but by freezing it instantaneously, we trap them in different orientations. So we're really just looking at the single molecule, but in lots of orientations, and by taking enough images, we can reconstruct it. And here's some beautiful work from some of my colleagues at Ohio State, where they've actually been looking at the drug paclitaxel, which is used to treat a variety of cancers. But its challenge is that it exhibits really poor solubility, and getting it into the targeted area is really a challenge. So my colleague Izon Du is an expert in designing RNA nanoparticles, and he was able to come together with some other colleagues to basically design a nanoparticle that would stabilize that paclitaxel and basically allow it to be delivered much more in a much more efficient way to the target. And what you see in the movie on the bottom right-hand corner is basically a 3D reconstruction from that single particle studied with cryo-EM to show how stable that structure would actually be, and helps us understand how we can actually improve the efficacy of such drugs. The final example is microelectron diffraction, and this is really a technique that is we're just learning from our colleagues in synchrotrons, where they would take large arrays of crystals and they would take them continuously and study the diffraction patterns. The problem with the synchrotron is you're averaging over lots of crystals, or in some cases you need really large crystals. In the electron microscope, we can see small crystals. Now we can do the same thing, but now we can identify single crystals, microcrystals to study. So here what you see is a study where we're looking at gold nanoparticles to aid drug delivery. And what you see on the right-hand side is a diffraction pattern taken as we dynamically turn the crystals within the electron microscope. And all of these bright spots that you see popping up here, these are the spots that tell us about how the atoms are arranged next to each other within that nanocluster. And by studying how these atoms are arranged, we can start to understand how they interact with other molecules, and then we can start to use that to inform how we can actually get targeted drug carriers for specific designer drugs. So we can really accelerate the path to drug discovery using some of these methods. And indeed, we were very fortunate that one of our alums from the College of Engineering, through a private foundation, gave us a gift of $500,000 to invest in this, particularly to tackle diseases such as Alzheimer's. And so I hope that I've given you a flavor of how cryo-electron microscopy is really driving forward our advances in cancer biology. It's allowing our researchers to freeze biomolecules mid-movement, to visualize processes, and that's important both for understanding life's chemistry as well as for the development of new pharmaceuticals. Thanks to the incredible detail of cryo-EM images and the versatility of the technique to study a wide range of molecules, it really is becoming one of the most popular tools for structural biologists to map molecular machineries within the cell. At CMAS, we're giving OSU researchers the training and access to explore the structure of proteins and the complexes that play such a crucial role in cancer using these cutting-edge cryo-EM techniques. And from such structures, scientists will be better able to understand the processes that help cancer cells survive and grow, which can lead us to new ways to treat the disease. Thank you very much.
Thank you, David. Appreciate the explanation of a highly complex and highly expensive instrument. And what I hear you telling me is that we can use the same technology of electron beams to examine the cancer cells, determine the structure of the drugs that we use, and then even develop a way to take the drugs that we manufacture to the cancer cells. We can do all of that with this technology.
Absolutely. You know, that's the power of these methods, that we're really able to understand exactly the structure of those the molecules that can be responsible for the cancer, but at the same time we can study the small molecules that can be used to treat the cancer. And then with the ingenuity that we have with our colleagues in engineering and in other departments within the university, we're actually able to take that technology and engineer solutions to improve existing drugs and to develop better drugs.
Yeah, and this technology, as you said, is very new and relatively rare to get a Nobel Prize for a new technology like this. But that probably means that there have been some unique breakthroughs that cryo-electron microscopy has enabled. Are there any that you can tell us?
Oh, I think particularly just it's evolving almost week by week. You know, the most recent developments are showing how we're actually now truly solving the structures of proteins and other macromolecules down to really down to the atomic scale. And that is really leading to not only, you know, advances in our understanding and treatment of diseases such as cancer, but in areas such as neurodegenerative diseases and many of the other challenges that face us as healthcare challenges in the 21st century. And it really is such an exciting area. We're one of the few universities that in the world to have such an extensive array of techniques on site that are accessible to all of our researchers. And that makes CMAS and OSU a really special place for this type of research.
Thank you, David. Also, thank you, Jennifer and Hussein. I'll now hand it back to Laura to open the floor or the screen for questions from our attendees.
Yes, thank you, everyone. So just a reminder to those of you who have been listening in, if you have any questions, this is your opportunity to use the Q&A function and enter those. If you do not see the Q&A button on the bottom of your screen, check under the 3 dots, the More button. Sometimes it's hiding under there. But we've gotten some great questions in advance, so we'll get started with those. So I would like to invite David and Hussein to join Dean Williams and Jennifer with your cameras on. Some of these will be directed in a lot of different ways. Our first question actually comes from Jim Dietz, who is a chemical engineering alum, and he is here with us today. Hi, Jim. Glad to see you on. Jim asks, he wants to know a little bit more about how engineering and medicine are collaborating in this new center and how it's funded. So maybe Dean Williams, if you want to start with that question.
Well, the center is officially opening, as we will announce towards the end of this meeting with a seminar on the 2nd of December. In the meantime, what we have been doing is between the James and the college, we have been funding postdoctoral researchers to help bridge the gap between the problems that come out of the cancer center, and the potential solutions that come out of engineering. So we're really in the very early stages of this whole process, but it's key to the strategy of the James for its future role, its future grant from the National Cancer Institute, and it's crucial to the College of Engineering for its future strategic plan. So really at the very earliest stages, a little bigger than needs an electron microscope to see, but still the opportunity to grow is really just starting. A very fertile field on both sides.
Thank you, Dave. Our next question is actually for Husnain, and this is from Tamara Anderson, who asks if your research can help patients with prostate cancer that has moved to the spine.
I would say yes, it is possible. It requires understanding the physics associated with the prostate cancer metastasis. Some forms of metastatic tumors may eat away part of the bone tissue, while others may induce immature bone formation. Both of them are destructive, but it is difficult to understand that, and it requires working collaboratively with cancer biologists to help us understand this phenomenon. So I would say it is possible, but it requires a lot of research.
Thank you. We have a few more questions about treatment that I'm going to pose, and if you find that they fall a little bit beyond the scope of your research, just let me know, we can move on. The first question is from Ron Butcher, who's an alum of Computer and Information Science, who asks if immunotherapy would be the holy grail, and if so, when? So whoever feels most like they could address that question, please jump in. Or maybe it's a little bit beyond our scope of work. Okay, we'll move on. Let's see, we have a question coming in from, this is a great question from Susan Dittmar, a mechanical engineering alum, who asked if Ohio State is doing any work in the area of nanorobotics to detect or treat cancer. So again, this may be one for you, Dean Williams, if you know anything about any work along that line.
That's not one of the areas that we are focusing on at the moment. You're hearing some of the principal areas that we have chosen to focus on that build on the strengths that we have. There is work on robotics in the College of Engineering in many areas. I'm not aware of the development of that at the nano level to help with the diagnosis of cancer. If there's anybody else on the call, either from the James or from the college that can chime in, then please feel free to raise your hand and we could maybe unmic you. So
feel free also, if you wanted to add anything in the chat, that would be great. And just a reminder to those of you who have posed questions, if we don't have the answers here, we'll see if we can get some answers for them for you and send those out over email later. I think this is last call for questions. We have one question in the Q&A from alum Doug Ball, who asks, how do we feel about the level of funding that you have for your research? So Jennifer, maybe we start with you to address that.
So funding is critical and tough to get. And so I think that that's actually where the Center for Cancer Engineering and things like Pelotonia, that's run by the James, is really important because it's funding these more new and innovative ideas. Federal funding like the National Institutes for Health usually wants to fund things that are a little safer and have more of a proven track record. So getting funding to really sponsor these new ideas that are more high risk, high reward is really important, and where these centers can help.
What about you, Dr. McComb?
Well, I think, like I mentioned, I mean, these electron microscopes are incredibly expensive, you know, and the single or high-end cryo-EM is, you know, near enough a $9 million instrument. You know, there are, as I mentioned, there are relatively few universities across the country that have those within their own facilities. So I think that we recognize the challenge. We brought together groups of individuals to apply for that kind of funding. As Jen said, it's tough. It's really tough to get funding, and especially at that level. But by bringing that group together, we really created a momentum that said this was critical to OSU, and that momentum just continued to grow. That eventually resulted in over 100 researchers coming to the reporting to the university that this was really going to be critical for the research. And fortunately, with the resources that OSU has at its disposal, we were able to bring together a consortium of 7 colleges and about 25 departments, as well as the provost office, to make this kind of investment. Now that then provides a platform, and that's really what we've now provided to our researchers across engineering and medicine, is to come together, especially in our Center for Cancer Engineering, is to be able to come together as a team to apply for funding to utilize these capabilities. And that advances their research. So yes, it's challenging to go and get the funding, of course it is, but we're in a much better place to get that funding because of the infrastructure that we now have in place. And that puts a great platform for us now to continue to build.
So you lead us to the next question in a really great transition. It's almost like you were reading the questions, David. So this one is from Dan Coombs, who asks, is this alliance between engineering and medicine at Ohio State unique compared to other institutions? And if so, does that help us attract more research funding and more talent in terms of faculty, staff, and graduate students? So maybe Dean Williams, if you want to start with that.
Thank you, Laura, and thank you, Dan. And no, it is not unique, but it is rare. There are interactions between engineering colleges and colleges of medicine and cancer centers in other institutions. However, it is rare that the medical facility or the cancer center is on the same campus as Jennifer pointed out, within a few minutes walking distance of the engineering college. For example, the Cornell's Medical Center is in New York City, and that's a heck of a drive from Ithaca. The joint engineering medicine effort at the University of Illinois, again, has a major separation between the hospital and the university. Penn State, a very strong materials and microscopy research effort, is, however, many miles away from the Hershey Medical Center. So what is the real strength that we have, apart from the excellence of the researchers, which I hope we've described, remember, just scratching the surface of the many faculty and staff doing this work. The unique part, or the very rare part, is location, location, location.
On that note, you were right. Location of Ohio State, there's no place like it, and there's no place like the College of Engineering for doing the work. I definitely want to take this moment to say thank you to you, Dean Williams, and to our speakers, Dr. Leight, Dr. Ahmadian, and Dr. McComb. Thank you for taking the time to share your research and help us spread the good work about what you are doing to our audiences, because it is life-changing work, especially for folks like myself who have been impacted by cancer, and many of you and your loved ones have. So thank you for being here today. I do wanted to let you know that if you have any questions about the Center for Cancer Engineering and anything that you heard here today, you are welcome to reach out to Sean Gallagher. Sean is our main liaison with the Center for Cancer Engineering, and he can connect you to informational resources. He would also be more than happy to have a conversation with you if you would like to support the work that's going on at the center. I'm also happy to say that though this was our first Engineering Cures for Cancer event, it will not be our last. We're looking forward to, over the coming months, putting together more programs just like this so you can learn more about the life-changing work going on by our engineering researchers at the Center for Cancer Engineering. As the Dean mentioned, the next event that you can go to with the Cancer Engineering and Center for Cancer Engineering focus is the virtual launch for the Center for Cancer Engineering, which is happening on December 2nd at 11:30. This event is free and open to the public. I will say it is going to be a little bit more of an academic research presentation, so it may be a little bit more academic and maybe a little less accessible than our speakers made their topics today. So, but it's definitely open. I would encourage you to sign up if you are interested in that. We also have some new opportunities to support the work that you heard about today or other areas of the college. So first, if you would like to make a contribution to the Engineering Cancer Research Collaboration Fund, you can do that right now from your phone. You can text the word engineering to 91999 and you should be able to make the contribution right there. And also, we are right in the middle of a special program for our alumni who have graduated since 2011, so within the past 10 years. It's called our Pay Forward Triple Match Program, where between now and November 25th, any gifts made by young alumni will be tripled thanks to the leadership and generosity of some of our older and more advanced alumni who are really excited about supporting the next generation of philanthropy. So if you would like to learn more or make a contribution, and again, that's to any unit within the college, that's to any student organization, anything that touches your heart, feel free to check it out. go.osu.edu/triple2020. You have a little over a week left if you want to participate in that program. And part of my role is to encourage all of our Buckeye alumni to network with each other. There's going to be quite a few opportunities to do that. First, you will be getting a roster of attendees from today's event. So these are people who have decided they do want to reach out and network with fellow Buckeye alumni and friends. So when you get that roster, I encourage you to make a connection with someone. You just never know where that's going to lead. Buckeye Nation is very strong, as I'm sure many of you know. You'll also be getting a survey about today's event, but more importantly, about what events you'd like to see in the future. This is where we want your feedback on what content is meaningful to you right now and what activities you would find valuable, so that even if we can't gather together in person, we can still give you some meaningful experiences in the virtual space. So please, please, please share your thoughts with us. We use those to plan for the future. And as you see on your screen, this speaking of future programs, this is literally hot off the press. We're really excited to be able to tell a very special Buckeye impact story. This will take place during Beat Michigan Week on December 10th, and we're going to showcase Sean Springs, who many of you know is a Buckeye football player and an NFL football player, but he's also the CEO and founder of WindPact, which is a company that designs protective equipment for athletes and military personnel. And the exciting thing is, I mean, that work in and of itself is exciting, but he's working with two of our materials science faculty members, and their research is helping him improve that equipment and keep these lives safe. So it's a great way to share some Buckeye spirit and hear about more of OSU alumni doing some great things during that Beat That State Up North week. So stay tuned. This event will be on our college event calendar very soon. If you are an alum, please make sure your email is up to date so we can send you that email invitation. You'll be among the first to know. And as I always mention, if you do want to be among the first to know about the great work happening at the college, please be sure to connect with the college's social media channels. We have extraordinarily good content out there on Facebook, on Twitter, on LinkedIn, and you can hear stories about students, about faculty research, about other programs. So if you are not already connected to our channels, we will send those out to you in the email that you get after this event. So with that being said, I thank you again on behalf of the college for participating, and have a very good evening. For those of you who celebrate, have a wonderful Thanksgiving next week. Goodbye, everyone.